we have this formulation. So if we think of it in the matrix form, right? Remember that when we had D and L, it became D cross L, right? So when we have both D, then it's going to just become D times D, right? So the recursive equation says D equals D times D with D0 equals L, right? What is L? L is this, basically, okay, L is this the initial, right? The initial adjacency matrix where instead of, you have the edge weights in that matrix, right? So if you have D equals D times D, right, and then you just do your iterative thing, so D1, right? So we substitute the initial approximation over here to get this next approximation. So D1 is D0 times D0 equals L times L equals L squared, right? D2 equals D1 times D1, right? And since D1 is L squared, it's going to be L squared times L squared equals L to the power 4, right? And looking through this pattern, you can see that the ith approximation is going to be L to the power 2 to the power I, right? Essentially what this is doing is, you can see that this is basically, so therefore what can happen is that if you want, so notice that we are going to L to the power 2 to the power I, and we know that when we reach L to the power n, we have computed the shortest paths, right? So that means I here needs to go to only log n, right? Because 2 to the power log n is n, right? So in this case, the iteration has to be repeated only log n times, okay? And essentially what we are doing is, computing nth power by recursive squaring, right? Yeah.
So here again we are using the multiplication as addition and min.
Right. In all shortest path problems, you're going to use that formulation. Okay? The exact same formulation doesn't change. Okay. So therefore, we know that this matrix multiplication, D is n by n matrix, right? So this multiplication is going to take n cubed time, but we have to iterate only log n times, so we have total n cubed log n time, okay? And this happens to be a variant of Floyd-Warshall algorithm for computing shortest paths, okay? And is good when the graph is dense, right? If the graph is dense, well, E, right, is going to be n squared, and so you're not going to get better than this, okay? In fact, if you look at the that's so if you look at the sorry, I might as well just take you to the previous slide, right? So if you take a dense graph, E will be n squared, so this will be n, so this will be n cubed log V, right? So running Dijkstra's n times is going to be yielding the same complexity as Floyd-Warshall in a dense graph, okay? In a sparse graph, Dijkstra's is actually better, right? But of course, you have to again keep in mind that this one doesn't have a limitation that of no negative costs, right? Edge costs can be negative in this formulation because we are not making the assumptions that we made in the Dijkstra's algorithm. So it is a bit more general, but it is remarkable that the all pairs shortest path, the simple-minded way of repeating Dijkstra's algorithm n times is giving you comparable efficiency as, or may even be better efficiency than algorithms that are purpose designed for the all paths problem. Okay, so that brings us to so somehow the fact that we are simply doing no better than running Dijkstra's algorithm n times tells you, it's just somehow it's not satisfying, right? It says that somehow maybe there is a better way. So let's try just one other approach, and then maybe we'll get there. Okay. So the main problem in the previous formulation is, right, it is this n cubed term, right? So each step is taking n cubed time, and then pretty much all of the complexity comes from this one step, right? Otherwise, you're just adding a logarithmic multiplication factor, which is obviously, amounts to almost nothing when you compare with n cubed, right? So if you want to improve the performance, you really have to get to this and make sure that this doesn't take n cubed time. Okay, so how do you do that? So the reason why it does that is because, again, so far what we have done is we have done a blind iterative solution, right? So we have an equation which is blindly, we know there's a standard way of, iteratively solving an equation. We just apply it blindly and then see what happens, right? And so, so essentially that blind application ends up, breaking recursion by limiting path length, right? So basically it says that after, one iteration, we have paths of length 1. After 2 iterations, we have paths consisting of 2 edges. After 3 iterations, we have paths consisting of 3 edges, and so on, right? And this way of breaking recursion, then you ask the question, okay, is there some other way of breaking recursion, right? Because obviously the graph has cycles, and that's why we have these equations which are recursive. And to solve them, we need some way of breaking this recursion, right? And the usual iterative technique is simply one way of breaking the recursion. There may be other ways. So one of the other ways that we are going to try is, why not, instead of saying edge lengths, instead of breaking recursion by limiting the number of edges, right? So we are saying that after k iterations, you only consider paths of length k. Instead, why not say after k iterations, I only consider vertices less than k, right? Why, instead of talking about number of edges, you could also say which vertices are going to be included in the path, okay? So this is the way we are going to break here. So we are going to say the shortest distance between u and v, okay, is, in this case, instead of breaking it on the length of the number of edges, k now represents the maximum numbered vertex through which the path will go, okay? So what we are saying here is that in order to go from u to v, right, you will go through, let's draw a picture. So you have u and v. So what we are saying is that we already know the shortest path. Okay, let's say this is vertex k. Right? So let's say this is a path, right? So clearly k will not occur here, right? In between, right? You're going from u to k, there's no point in going through k in order to get to k. Similarly, to get to k, v from k, once again you don't have to go through k, right? And in addition, what you're saying is uses only vertices 1 through k minus 1. Okay? So what you're saying is that the question being asked is, what is the shortest path that doesn't go through any vertex higher than k? Okay? So this represents the shortest path from u to v that uses only vertices numbered k or below. Okay? So essentially you're saying I am arbitrarily going to ignore vertices that are numbered higher than k. Okay, I only am interested at this point in computing shortest path from u to v that only goes through vertices up to k. Okay? Now, in the previous iteration, you have done this same thing. You have solved the same problem, right? But you have limited yourself to vertices numbered 1 through k minus 1. Right? So what you're saying here is that in order to find a path going from u to v, right, that uses vertices no more than k, right? So vertices 1 through k can be used in this path, right? du uvk represents a path going from u to v where the intermediate vertices is one of 1 through k, right? So if you can use only 1 through k, right? So then there are two choices. One is that you know the shortest path doesn't even have to go through k. Okay? So that's what this one says, right? Maybe you don't have to use k, so you can already get the shortest path from u to v by going only up to vertex k minus 1. Okay? Or the shortest path must go through k. In that case, you need to somehow get from u to k and then from k to v. Okay? And since this whole path contains only 1 through k, and since k is already here, right? So this path and this path should use only vertices 1 through k minus 1. Right? Because if this whole set is 1 through k, and k is already here, then these must be 1 through k minus 1, and these must also be 1 through k minus 1. And you already computed the shortest path from between u and every vertex that uses vertices less than k minus 1, right? And so by breaking the recursion this way, now you have a better algorithm. And why? Because let's just go through this. So once again, this k, when you let k go to n, right? Then this is no longer a limitation, right? Because what you're saying is that you go from u to v using vertices 1 through n, which means that you can go through any vertex. So by the time k reaches n, you have actually computed the shortest path, right? But in the path going to n, you have some quantity, right? We don't know exactly what it means, but it is something that helps you compute the final solution. So you have to do this equation n times as k goes from 1 through n, right? So you have to do this computation n times, but each time you need to only consider a particular k, right? So the k is fixed here, right? The vertex k is fixed here, whereas in the previous thing we had u, v, and w, right? So there are n choices for this, n choices for this, n choices for that, and that's why we had an n cube algorithm there. Whereas here, k is fixed. You have only u and v that are not fixed, which means that u has n choices, v has n choices. So there are n square choices. So for each iteration in this form of the equation, each iteration takes n square time, right? But it doesn't take n cube time. So now n iterations, n square time, you get O of n cube algorithm, right? Which is better than O of n cube log n, right? So the last algorithm we had was O of n cube log n, right? So we had n cube log n algorithm here, and it's now by breaking up the recursion in a different way, we have eliminated that log n factor, and we end up with overall O of n cube algorithm. Okay, so
in a way, can we visualize this as we are now considering only vertex pairs, edges that are included in the graph or something like that, right?
No.
Edges at a distance of within k.
No, not edges. These are vertices.
Vertex pairs.
No. Again, u and v always range over the n vertices. Okay? What we are saying is that on the path from u to v, we are going to limit what vertices can be visited in the path from u to v, right? the first iteration, we are going to say the only vertex you can visit is vertex 1. You can go from U to 1 and then 1 to V. The second iteration, you're going to say you can go from U to 1, 1 to 2, or U to 2 and 2 to 1, and then to V, right? So that way you can go through those 2 intermediate vertices, right? In the third iteration, you can go through 3 intermediate vertices 1, 2, and 3, right? So, and so on. And you keep building your solution this way. And by the time you allow yourself to go through all n vertices, you have actually completed the shortest path. Okay, so now let's summarize what we have done. So we have been talking about dynamic programming. So the essential step, right, the most important step in dynamic programming is this, right? Everything else is relatively mechanical, right? The first thing is really understanding the problem and setting up this equation that says, okay, the optimal solution to this problem can be computed from optimal solution to certain subproblems, right? So you set up that equation, and that's the crux of the problem. Recognizing that there is this structure, that's really, so when you have to, if I give you a dynamic programming problem in your homework or exam, it's really, this is the step that you need to really focus on. What is the structure? Because once you have the structure, the rest is easy, right? In fact, what I'm trying to illustrate with this iterative formulation is that there is often a mechanical way to take this equation and unroll it and solve it, right? So there is a mechanical procedure for solving the equation once you know the structure, okay? And when you follow that mechanical procedure, you may actually along the way find, you know, the mechanical procedure can be improved, right? And then get better performance than what the dumb iterative procedure for solving the equation will give you, okay? So in particular, we considered a number of problems where the underlying dependent structure is acyclic, right? If there's no cycle, well, then there is basically a dependence graph is a DAG, and then we just do a topological sort on that, and then we do this evaluation or solve this equation in a bottom-up way, right? So this is what you see typically in most dynamic programming problem. The underlying structure is non-recursive and it's simple. But in some cases, you have a recursive structure, and the way you deal with recursion is essentially by introducing additional parameters to break recursion, okay? And the fixed point iteration technique that we applied on graphs essentially was breaking it using the number of edges, right? And then what we said in the very last slide was that, well, there are other ways to break the recursion, and you know, you can actually use any way to break the recursion and use that to solve this original equation. But again, the key is always this, right? So once you realize that that is the key, and not get too bogged down in the other details, right? These other details you can always pick up, but that's really the crux. Knowing that there is the structure, and then you can apply dynamic programming to solve that optimization. Any questions? So how was the exam? Was it? So the